So, good afternoon. Welcome again to Concept Colliders. This time it's going to be a topic about own causality. So I'll remember to the audience that we are bringing certain topics from the three main topics of our upcoming summer school. By the way, you can already register for that. It's going to happen in next July in Valencia, in Spain. So the three main topics of the summer school are causality, cognition, and rigor, and anything that fits within them. And this is going to be, this specific concept collator is going to be about causality. And more specifically even, we're going to discuss, debate, talk about whether we think that causality can be reduced maybe to just asymmetric information flow, asymmetric information exchange, influence between nodes in a system, between systems. By the way, before going into the debate colloquium, just a brief reminder of the structure. So this is a more or less semi-moderated discussion. So you have the timers there. We are going to try to restrict just a little bit if needed, but I try not to. The time for in which each person intervenes. We will divide the main event into mainly two or three subsections, depending on the kind of questions that arise. I have several possible questions for you to delve into prepared, but of course it's also up to you to engage in one or the other. And then first of all, just a brief introduction, and then I'll go over. I'll leave you, each one of you, to just do a brief intervention. Just tell me your thoughts on what I said, or just on whatever side topic that fits into this question that you think about. So yeah, the main introduction is just to settle how important this is. So, and how subtle, both scientifically and philosophical, this question is. Of course, causality and the idea of cause and effect as a temporal asymmetry comes back to Aristotle and several Greek philosophers. Not only in the Western tradition, I always try to remind this and tell people about this. Eastern philosophies have delved into these kind of topics for a long time, and there's always, as far as I know, at least in my experience on searching information, there's always an equivalent of the same kind of concept or debate within Taoism, within specifically Zen philosophy, within there's many schools of Hinduism. So let's consider that also. So the directionality of time is one thing that seems very obvious, maybe. And of course, in physics, we have the these are one of the interpretations. But for example, the interpretation of the speed of light as a limit to the speed of causality or causality influences between systems. There's of course the time arrow that entropy allows. That maybe it's the main implementation. I don't know. Then there's something that is quite applied within now at least social sciences, but also, and quite interestingly to me specifically, in neuroscience, the causality model. So there's Friston dynamical causal modeling. There's Julia Pearl's structural causal models, and in those kind of models, there's also like a type of directionality of causality, that's for sure. And that's, by the way, why they tend to use a cyclic directional graphs, not cyclic directional graphs, because that makes it way more difficult to infer a clear causality set of relations. But at the same time, there's the idea, rising idea, that in a very abstract definition of causality, and there's the idea of a model, mechanism being subjacent to several phenomena. That's enough for causality in principle. And that kind of very abstract definition of a mechanism maybe requires pseudo time in the sense of a hierarchical relation between mechanisms, but not necessarily maybe a clear uh, time asymmetry and time flow. Of course, that's necessary for things to happen, things to evolve, but maybe it's not that important. Maybe the idea that there's a parallel mechanism subjacent to several phenomena is enough for causality. That's one of the things that I wanted to bring on the debate, and maybe the most difficult, most daring question regarding whether asymmetry is intrinsic to causality or not. So yeah, just go on, Danny, if you want to go first, but there's no strict order. Also, Martin, if you want to go, whoever wants to be first.
I would like to listen to what other people have to say first,
Okay,
and maybe
so
engage with their thoughts.
okay. So Martin, if you want to go first.
Okay, so I've got actually quite a different perspective on causality than is normally taken, which is that if I look at history, history is something that always accumulates. So we develop historical records. We learn from things that have happened in the past. And in fact, the past is essentially our information that we hold in the present, and we order that information. So with all the information we have has this notion of a temporal order. Things that occur later are always consistent with what happened before, right? So we've got this relationship that we maintain consistency over time. Now, as time progresses, we learn more things. We actually gain new information that we didn't have before. This is largely consistent with what happens in quantum theory. That and there's a whole theme of the question is quantum theory an epistemic theory or a ontic theory? And the epistemic approach, primarily we're looking at it and saying, well, we have information about the past, and based on this information about the past, we'll make predictions about what the possible outcomes of the future are. And when the future comes, well, we'll have a new outcome. All right, we'll have added information. And so we've got a progressive accumulation of information. And that new events, new information coming into our history is what time is. So time is not something that exists that drives things forward. Time is we're learning new things, and we're learning about the universe. And as we add new information about the universe, the configuration of all of the rest that we've got has to change. Our space-time model of the universe has to evolve in order to incorporate the new information without invalidating the prior information. Now, you can't turn that backwards. All right, you can say, well, what was it like earlier times? Well, we had less information at earlier times, and I keep going back. If I keep taking information away and I go back to an earlier time and an earlier time, eventually I get to the point where I've taken all the information away, and that's the start. That's the origin of the universe. There was no information. And so the development of space-time is actually an accumulation of information. And the question is, who has the information or where is it? And that comes to the whole questions of mind and consciousness and so on. And I can't solve that problem. But I'll just leave it at that for now.
Well, before carrying on to the next ones, would you say then that your idea is equivalent to the idea of time being just related to the amount of change? Because of course, if there's no change in the universe, no information is added, then there's no time. Would you say that?
Yes, but it's more than change. It's actually change, which is always accumulation of information. So if
Yeah.
you want to run time backwards, you have to take information away.
Yeah. So, and one last thing. So, would you say then that information is like must be created, but must not be, but cannot be destroyed? Because if information is destroyed, then you go back in time. I
Uh,
mean, will you say
yeah,
that or?
Yeah, I'll say that, but my notion of information, if you want, includes all of the microscopic details that normally we think of as entropy. All right.
Yeah.
So it's the microstate. So the microstate is evolving. We can't access most of that information,
Yeah. Yeah.
but it defines the universe and it defines the geometry, everything that we see.
So great way to to begin with. I love that there's as to say outlier interpretations, because yeah, like it's very easy to just say, oh yeah, time is a flow that is out there, and it's an asymmetry thing, and like regarding cause and effect. But what is that actually? What's the I won't say ontology, because I don't think, I just think that there's an epistemology, not ontology, but more deeper, deeper. Daniel, if you want to go, or Fadi.
I mean, I'm kind of reminded of like an idea I had in one of our conversations when I was there at
Oh,
you
yeah.
guys' place. Um, um, and it was like something I'm not sure like how you would make this like physical, or how you would make this more akin to something which you would discuss in physics. But the idea of instead of saying there was a starting point, or saying there may be a starting point, but the time doesn't just go in one direction, but it is bidirectional in some sense. Combined with the idea that maybe the actual past states of the universe, or at least of some systems, is in some micro sense accessible. Um, so you can in some way navigate it maybe, or that the dependence on previous states is not just previous states, but how far back in history you go in some sense. Um, so in the sense that the past is not just a static thing, but it's also just accumulating information in the other direction as well. So that like what Martin said maybe reminded me of that. Um, I don't really have much else to add to the conversation, so I was just hoping to like listen a bit and then see if some thoughts popped into my head. But just generally more about the observation, like some abstract thought I had about symmetry or asymmetry, just in general, not necessarily relevant to causality itself, is more that in order for us to observe causality, or this asymmetrical information flow, if that is indeed what causality is that the more um, uh, in some sense, the more symmetry there is, the more asymmetries you need in order to keep track of it, and the other way around as well. The more asymmetries there are in the information, the more symmetries you need in order to keep track of it. So it's always this like sort of dichotomy or something you would call it, of having to observe the asymmetry or the causality of the system.
So I will there. I will about the first thing.
Mm-hmm.
I will say that maybe that's just it's a question for you.
Yeah, yeah.
Would you say then that maybe your idea can be equivalent to saying, okay, if we have a very pragmatic point of view, the memory on of your system can vary, of course, and you can, and not only the memory, you can like the accessibility of past events, as to say, even for example, the trying to infer the causes, for example, of previous events. If that can change, sometimes it's more or less accessible. That means that in practice we are, epistemologically speaking, traveling in time. So that there's a, will you say something like that?
Yeah, yeah, I think so, yes.
And about the second thing, I would love if you all want to go to the later on that, or maybe now, I don't know. It's just
No, we
I'm
can
going
go
to
later on
mention it.
that. Yeah.
Yeah, no, just that this, your second thing is quite interesting to me, because it relates to this idea that a microscopic reversibility is quite compatible with a macroscopic irreversibility. Martin, yeah.
The macroscopic is, if you want, that's the very firm history that we've developed. So we've got this model of the world, and that model has to be preserved. This is if that model changed abruptly, then that would be like, okay, we're today on Earth, and then an instant from now we're somewhere else, or things are completely different. So we have to have this notion of stability. What we're doing is we're building this very robust model that's reliable, and that is our historical record. And all the changes, the microstructure the changes cannot change that fundamental model. It's all the little details that change. And so the model adapts in order to incorporate those new details.
So you will say that the universe is more stable in the high level than in the low level.
Yeah, because that's the way our minds work. We develop, in our mind, we develop a model of the world. And what goes into that model is what's stable. It's way into the model if it doesn't persist.
Any thoughts on that, Fadi?
No, I just agree with it.
Okay. So Daniel, your turn.
Okay, this was making me think of the double slit experiment when the observation is after the particle has gone through allegedly through the slits, and the different theories that you could make to actually explain the phenomenon. And so like you can either define it as, okay, like the information is not there yet, it's kind of like it is in a specific thing, it's not yet defined, so when you measure it, then it's actually when it's defined very specifically. Or you can think there's some retro causality or whatever. And I guess like to me, I can't for now, maybe you guys can help me out with this, but I can't tell which one should we favor, like, because I guess one of them would break our conceptions of physical reality, our usual understanding of reality in one way, and the other one would do it in another. But at the same time, I think, like, can we, even if we can explain, we can maybe like hand wave through this and favor one theory or another. Can we actually tell the difference between these two possibilities instead of just favoring one, which is the one we are most comfortable with? So like, I guess the way I would deal with it is like, if a question is undecidable, of you can't really choose one theory over another, then it would be best to choose a theory that's neutral enough to not tell any of these other competing theories to be right or wrong. But yeah, I mean, I guess this kind of experiment can put you in a situation where you're like thinking, okay, can there actually be causality in the other direction? And what would that mean at all? I don't know what you guys think about this.
One take that I like from a speaker from the last summer school, by the way, is Jacob Barandes. I don't know if Martin, if you have heard of him, Jacob Barandes.
Yeah, I've done some reading on his work.
Yeah, and it's quite interesting. Like the idea, at least to me, that maybe all these abstract configuration space in the Hilda space and all can be reduced, maybe, and the collapse of the wave function, all those things maybe can just be reduced to the idea that before the collapse, there's some memory in the system. There's like maybe reality is working more in parallel, as to say. So it seems that it's more interconnected or something like that. And in my neuroscience language, I will say, yeah, like more function of working more as a parallel system. And then after the collapse, in the more classical way, it becomes more sequential. So it hasn't that much of bandwidth to store information in parallel. That's an idea that maybe relates to what Danny was saying, and that, to me at least, it will solve maybe this. Yeah, this not the fact that it's not retrocausality, whatever. It's just that there's something temporarily shared, especially when the system is very isolated. It can exist, it can coexist in that sense, but then it collapses when it turns very sequential to another very sequential state when the environment is more noisy. Yeah, Martin, go if you want. Yeah, I'm curious about your.
Okay, so a lot of the problem in quantum theory is actually the definition of a system or a subsystem, because formally in quantum theory, there's just one state of the universe, and it's
Yeah.
it has no subsystems. We have the measurement problem. We don't have any observers. They're all part of this one system, and so it's a real mathematical challenge. And this is the big problem in general in quantum theory, is the measurement problem. We try to think of quantum theory as something that's independent, it's on its own, and typically this is an ontic thinking. We think of it as being a mathematical truth. But we actually never observe any of these intermediate quantum states. Before the collapse has occurred, we prepared a system, and we say, well, we can do a measurement. We might find spin up or spin down, but we haven't done the measurement yet, so we don't know what state it's in. But we like to think, if you have an ontic view of things, that there's something real there. Whereas what I'm suggesting is that actually the quantum theory, if I think of it as an epistemic theory, it just allows us to predict the future. But what quantum states are doing is they're describing what we already know. So this is your preparation. You've got a classical, I'll call it, or a quasi-classical apparatus, and you prepare a state. So that state is a description of what you already know, the information you've got, and you're waiting for the information you don't yet have. And you can't actually talk about anything happening in that particular subsystem in the intermediate time. Well, how do you know that time is progressing? The rest of the universe is evolving. Your clock is ticking. All kinds of other things are happening. Those are all the classical universe is evolving. All this how it's going on around, while your particular state you prepared doesn't participate in that, and it can't give you any new information until you make an observation and you find out what the state is. That you've gained some new information.
When you say that okay, yeah, that there's so the measurement, for example, Jacob Barandes will say, and this is not because I love Jacob Barandes. This is also my this was my intuitive idea before knowing about him. That maybe just there's no need for a specific concept of measurement, in the sense that measurement is just interaction, like in that sense, for example, a system that shows quantum properties is quite isolated, and when we measure it, that's a way to say that we are sending noise to it, that we are de-isolating it, and then there's a change in the system that adds new information, and that's the
Yeah, this is the whole notion of decoherence. I strongly recommend reading Zurek's papers from, I don't know, 15 years ago or more, where he explained, that how decoherence occurs, observations get made, we end up with pointer states, classical observations, and then the whole notion of quantum Darwinism is that these states are evolve as persistent states in a natural way, that they're emergent, and so we gain information. But what we're gaining there is, if you want, the macroscopic information. So I've measured a pointer, so I've got a macro measurement. The micro state I still don't know. All right, that pointer has got all kinds of microscopic details going on within it that I have no idea what they are. So we can only see this very coarse-grained view of things. That's the information that we can take in. But the universe is still doing other things. The atoms are bouncing around in the air and so on.
Yeah. What are your thoughts on this, Fadi?
Not that many.
Not in the sense that he's not thinking of anything, but the opposite, I guess, because he's always thinking about several things at the same time. Would you say that, for example, regarding trying to get back to the specific topic of time, would you say that maybe then that the macro aspect of this of things, the more cause aspect of things, then has a more intrinsic timely nature, but in a very macro sense, there's a loss of that kind of thing. This may be related to what I was also mentioning before, like entropy, like according to some authors, entropy actually requires reversibility in very macro scale, micro scale.
Micro scale, yes.
Yeah. So I don't know if that's.
So our laws of physics, both quantum theory and classical physics, are deterministic. So they're time reversal symmetric. The wave function, the Schrodinger equation, the Dirac equation, so on, they're time reversal symmetric. And all our classical theories are as well. So you can turn the clock backwards and you can't tell the difference. This is the major gap in physics. It's the measurement problem.
Yeah,
We
I
don't
agree.
know what determines the direction of time. Now, if you look at entropy, we know that what you're dealing with is a very large number of potential degrees of freedom, and the system is going to evolve to one in which you've got more disorder as opposed to having more order, and that's the direction of thermodynamic time. And so, yes, the thermodynamic time typically is going to align with our clock time, and that's somewhat consistent with classical physics. But classical physics is time reversal symmetric, but measurement is not. I mean, that's the piece in quantum theory that's not explained, that says, okay, so we make a measurement, we gain some new information, and that's not time reversal symmetric. So that's the only piece that's not, and that's the piece that's been a mystery for a long time.
Yeah. If Daniel or Fadi, do you have any other opinion on this because I was going to interview him, but before.
No, I was just
No,
wondering,
no.
are you actually just is it because you're actually interrupting some other system which is doing things on its own, that you just destroy some history or something in interacting with it or something? So is how I'm thinking about it.
Yeah, that's kind of a bit of the intuition that I have. Not necessarily history, but as I said, like this I imagine that there's a variable bandwidth of memory capacity in systems. That's at least one of the intuitions that I have. And when you interact with it, when in general, when there's more interaction between systems, then that collapses, that is reduced. There's this equivalent. I want to think equivalent in what we think about the brain, in which when arousal, cortical arousal, for example, but in general, physiological arousal in the nervous system is lower, your your memory capacity, like the bandwidth, at least, the parallel capacity is higher. And that's the opposite. In the opposite happens when arousal is higher. And you can very intuitively think about this situation in which you are very anxious and you run between rooms or whatever, and you are not. You may do you still see my camera, by the way? Because no, okay, sorry.
Not yet.
You lose memory width and in that regard. But even when you are quite anxious and when you are very proactively thinking about things, actually your sequential memory is not that bad, because actually you are trying to plan ahead. You are trying to remember, oh, I had this task now. Tomorrow I have this other task. So that kind of trade-off is the one that I'm interested in. That I think that maybe exists in general in physics. So, of course, not because the brain is special, but just because the brain is implementing physics. That's one intuition. So, for example, to connect with your previous intuition, maybe that like the past, like going to the past thing is related to the sequential memory of the system. I'm, by the way, Martin, quite interested in in thinking about Markovian versus non-Markovian systems. And Jacob Barandes was mentioning this in his talk. And I do think, of course, that also the brain adjusts how Markovian or non-Markovian it is, depending on the situation. So yeah, any other ideas on this from any of you?
So this question of bandwidth and how much we can incorporate is quite interesting, because clearly there's an awful lot going on that we can't resolve. We can't see the motions of all the atoms in the air, and we have this finite capacity. And so what we're doing is we're developing this very, very coarse-grained model of things, and that's what we can commit to our memory. And to a large extent, that's inherited. I mean, so our relationship to the world is, right from the time you're born, you cry, or there's all of these things that happen that are just, genetic. They're built in, and so our memory is really a result of hundreds of millions of years of evolution. And it's not something that we start off fresh and, we learn these things, and it's built into us. It's very complex, the way in which it's encoded, and that makes it very robust. So the robustness of memory, I think, is very important. This is a piece that's totally missing from physics. Physics doesn't say anything about historical records and the preservation of records. When it talks about deterministic evolution, there are no records involved. It's just, it's like we have frozen time, because the future is absolutely determined by the present. That's not the way the real world works. So this is a big gap in physics, and I think it needs to merge in with neuroscience and other areas to really understand what it is we're doing.
Yeah, exactly. Do you have any? Oh, by the way, to reconnect to the topic at hand, I will say that there's, for example, with this thing about parallel versus sequential capacity. To me, for example, in many of these new recent structural causal models by Julia Pearl, for example, but not only from him, it just in general this progressive idea of mechanism as causality, like causality is a mechanism subjacent to a phenomenon. There, I can imagine that you can think of a hugely a very rich set of parallel dynamics. So even if every specific interaction between the things, for example, is like 1, 2, then 3, then 4, it's not clear that there's a causality within these subsystems. So then there's no causality in practice. And of course, like, since I try to think always in terms of keep with this epistemology and whatever other metaphysical thing that's riskier, whatever, then I will say maybe causality is literally weaker when the system is inherently more inherently working more in parallel. That's all another idea that I have.
Yeah, I was thinking this when you were mentioning parallel versus serial, because so it feels that at least when we talk about causality, it seems to be about a serial kind of way of thinking, in the sense of that things determine each other, kind of like dominoes falling, rather than a more ecological kind of just the things how they are, and they're like flowing and changing in time, and then it just turns to be like that because of some lots of statistically related things. I guess it also I don't know if there's a limit to this logic, because as a cognitive agent, you can maybe formulate parallel networks as serial, and then basically you turn a bunch of things happening in parallel as one object, and then it seems to be like there's some causality in there. just because you're conceiving a very complex system as one atom that's interacting with another. So I guess there's also a limit to what we can, like, causality in some sense is just a way that we use our brains to make predictions and model the world that is somewhat asymmetric and somewhat simplified, I guess, and serial in nature.
You were going to say something, Martin?
Well, I agree with that. I think that we, in developing a model, if I think of causality, it's not that we are causing the future, but the future needs to be consistent with the past. In other words, we're not allowing a future to our system to evolve into a state that is inconsistent with the past, because the past is part of this very firm model that we've developed of the world, and we can't contemplate an evolution in which the past simply abruptly changes and becomes inconsistent because we've added some new information to it. So the new information has to complement what we've already got. It has to fit in, but it can't disrupt. It changes the way things are configured, the positions of things. If you knock two balls together, they're going to interact, but that's all consistent with what we've learned in the past. And so instead of causing the future, it's not determining the future, because the future is going to be different, but the future has to be consistent with the past. And that's the main thing. So kind of the word causality is kind of wrong in the sense that it sounds as though we're causing the future. We're not causing the changes that happen. The changes are just going to happen on their own, and we'll learn about them, but they have to be consistent with the past.
Do you have any idea on this, Fadi? Maybe from computer science. He's very keen onto that.
Maybe in a bit.
Okay. I will. I was with the last intervention of Martin. I was thinking on this idea of it's a bit difficult, maybe difficult to no, maybe it's not difficult to express. So basically, I have this idea that maybe what we think about entropy and part of information theory applied to thermodynamics and things like this is quite like epistemologically tautological, in the sense that maybe the progression of our knowledge is exactly what we are describing with this increase of entropy. For example, maybe this is stupid, but for example, imagine, so if we understand entropy as the progressive increase of this ratio between the number of micro states versus the number of macro states, that maybe means that, okay, we are adding information, there's new events happening and so on and so on, there's new dynamics and so on, but we are progressively restricting them more to a consistent model, and that's the denominator, that the lower in relation to less amount of fewer macro states. That's one idea that I have. Maybe it's very, very, very tautological in this sense, and then our epistemology is, and then our science and so on is restricted to this kind of logic. It's also because there's like entropy appears in like the despite this determinism, this overall determinism. Entropy appears somewhere in, for example, in the minimization of change of action in quantum mechanics, also and also in general relativity, for us to know where the system is going to go, what's the preferred path of the system. So there's some, even if we have not integrated that much, like thermodynamics, into all these theories, I will say that at least it's already telling us, it's already been useful for telling the system, for telling us what's the best thing, what's the preferred paths of systems. And that, I think, tells us what's the logical, what's the consistent, what's the most consistent uh, path that the systems choose, and that's the future. That's one idea.
Yeah, the future is going to be the most disordered state, and the macro variables that describe that state will be the fewest in number. That's basically what you've said. The puzzle that we've got is that we are, in our minds, are highly ordered states. So as our bodies are entropy machines, we pump out entropy. We take in, low entropy materials as best we can, the foods and so on, and we pump entropy out. We throw it away in order to maintain ourselves as low entropy ordered states. And we're doing the same thing with our computers. All right, we're trying to organize the information as best we can to get rid of the disorder. Our computers are voracious consumers of energy, and they put out heat. That's the entropy that's being thrown away. And this is the process we got. So the question is, how did we evolve? How did our minds get to this state? And we're using our minds and so on in order to invent machines that also behave in a similar way. But we're developing these models of the world, our theories and so on, by creating ourselves as low entropy islands within this large universe. And this concept of time may be just something that's peculiar to intelligent beings.
What do you think on this, Fanny? Do you have any insight or doubt or concern?
I mean, I'm kind of stuck on a few things. Like I'm stuck on the thing you said earlier about two things. One, where I'm stuck on is the thing you said earlier was the more parallel processing that's happening. Basically, the more it's like disconnected from causality in some sense. You said, or something like that.
Yeah, like
So
that we can say that there's less causality, as to say, if we understand causality is intrinsically sequential.
yeah. Yeah, but would you say the same thing about the the parallel branches which are happening, because they are still sequential in themselves?
Yeah, and that's something that Daniel mentioned before. Like we can change the way that we can exchange, better said, we can exchange the way that we describe a parallel system as a sequential system and vice versa. Yeah, exactly. So very good point. Thank you for bringing this. And you can follow with the second thing you were. My idea is that maybe there's this intrinsically non-reducible to sequential parallel thing. So, for example, you cannot say like rigorously, or at least better said, efficiently, because I think it's just think about efficiency, efficient descriptions, not. You can. It's way better to say that when you move, or when you change the structure of of a Rubik cube, uh, it's not that each part of the Rubik cube is sequentially telling another part of the Rubik cube to move or whatever. It's a structural relation, so things are intrinsically happening in parallel. When you move when you move a surface, it's not that every point on the surface is sequentially communicating with the other. If there's a structural relation, that's a parallel phenomenon. So, and maybe, just maybe, this is the same thing happening with quantum entanglement. It's not that there's a faster than light communication between the two pairs. It's just that there's this correlation already created between these two subsystems, this pair of thingies, as to say. And that's why we get we get information when we access the state of another. That's at least my idea on this.
Mm-hmm.
So on that, this question of entanglement, we prepare an entanglement state using again, classical apparatus. So we prepare the state. So the information that's in there, we create two particles that are entangled.
Exactly.
That's the information that's classical information that we used in order to prepare that state. And we call it entangled because we don't know what the outcome of the measurements, future measurements are going to be. But the ultimate entangled state, I think, is the world we see around us. We are intimately entangled with everything else that we see. And we're entangled by virtue of the electrons that are flowing back and forth in order to enable this Zoom call. And so the entanglement in what we see is so enormous that we can't disentangle it. The world that we've got is a consequence of all of the entanglement of all of the components that are going together. And when we prepare one of these special, classical quantum subsystems that's an entangled pair, what we've done is we've carefully disentangled those from the rest of the universe as best we can. And so now we can say this pair is not entangled. They're entangled with each other, but not anything else, not with anything else. So that's the special case that we're creating, and we have to think of quantum states as being the subsystem. Is it something that we put this great effort into disentangling from the rest of the world, whereas entanglement is the normal situation.
And by the way, we have a new member in the call. Hello, Michael.
Oh, hi. Sorry,
No,
I forgot that this was today at this time.
It's fine. Thanks for coming. That's I just send for all of you. I just send another message in the on the Discord, because some people in within the Discord don't know that they can actually join the calls. So I always try to remember them. Of course, anyone can also join through the YouTube streaming, and I try to pay attention to the chat in case anyone has a question or whatever. But by the way, I wasn't since we were such as so few. I was not checking the timing, but I can add Michael now here, and I'll try to finish the event more or less about half an hour. Of course, earlier if we are okay with that. But yes, so I think that 5 minutes is better for all of us. So Michael, any comments on whatever? I don't know if you had anything from before, or just comment on the main question. Your thoughts on this?
This is like about what causality is.
Yeah, so then for a bit of context, basically, specifically within causality, we were trying to understand, debate whether asymmetry, and specifically temporal asymmetry, but in any case, until which point any kind of asymmetry is related to causality. Because of course there's this historical intuition that supports this, but at the same time, there's the idea that maybe there are parallel relations happening in the universe that are already also storing information in that kind of sense. Also, there's this idea that maybe it's not necessarily temporal asymmetry. Maybe it's just asymmetry in the way, in terms of mathematical objects interacting with each other, but within a mechanism, and that mechanism is implementing changes in phenomena, and that mechanism is the cause of the phenomena changing. But then there's no necessarily intrinsically temporal asymmetry. The mechanism is has several pieces that are interacting, but it's not necessarily that there's a sequence of phenomena, because the phenomena are already being caused by a mechanism. So then it's not intrinsically temporal. This is the summary of that.
Okay, so I think I have an extremely poor understanding of what causality is at the moment, because imagine you have a slice of a solution to some kind of partial differential equation, and you evolve it like forwards like over time. Basically, what you're doing is you're using the PDE to like solve for what the time derivatives like should be for all the like spatial derivatives, like most importantly the zeros one, and then you're kind of analytically continuing it like a certain point forward in time. That's all that you're doing when you're evolving something. But if this solution was entire meromorphic and it had no like branch discontinuities, then you could have like a single point, all the derivatives at that given point, like and you could take all those derivatives and use them to analytically continue the solution to any other point in the coordinate system. And you could then do it like backwards as well. And from that perspective, like every point's essentially perfectly correlated with each other and contains all information about all other points. And like, can you really even label a cause and effect at that point? Because like if you were to try to, then perhaps like every point would be the cause and effect of all other points. So I don't know if I'm thinking about like causality correctly.
I think so. Like an equation wouldn't necessarily tell you about cause, but it would tell you about. It would make very good predictions about what's happening, what kind of how the values are changing, but not necessarily give you an understanding of how these variables are related to each other. I think causality is more about a necessary relation between variables. So if you manipulate a specific variable, then that will lead to some other change in some other variable. And for that, you need a notion of manipulation, of actually being able to go there, manipulate that, change that, and then see what happens, or at least some abstract toy model that tells you the relation between these variables, and then you can do that with this toy model. But if you have an equation, the equation is just a relation of variables and doesn't tell you anything about the causal relation, if it exists at all, between these variables. Just tells you that there's an intrinsic relation in terms of values, but no more than that.
Yeah, you could, like in theory, have an observer inside of the solution, like some kind of like computer able to like see what the field values are around them and then like act accordingly. So then they could like take actions. But again, because the entire solution is like entire meromorphic, you could kind of just evolve it like forwards or like backwards in time in all kinds of directions. And it like just works regardless. So yeah.
So
Yeah,
there's
go, go, Martin.
I was going to say there's a bit of a fundamental problem here, I think, in that in physics we have since Newton made use of real numbers, real functions, or complex, doesn't matter. But presuming that one can define numbers with arbitrary precision and that the real world is somehow in direct correspondence to these real numbers, in reality, we can't measure anything with arbitrary precision. I mean, a real number has an infinite number of bits of precision. The universe contains, if you look at the cosmology, about 10 to the 90th bits of information in the whole universe. And so the universe doesn't have enough information to specify one real number. And we develop these models and we presume that we can use models and take derivatives and arbitrary numbers of derivatives, but that's all kind of it's a mathematical thing. It's not the real universe. And so we have to really differentiate between what our models are and the properties of the models and how they relate to the real universe. And that's a serious problem. That I think we have to start stepping back and say, okay, so what if we don't use real numbers? What if we use distributions or make everything fuzzy, then what can be done? And I think part of what quantum mechanics does is to do that, is to start making things fuzzy.
One idea that like to link this, to try to get it more real. Daniel was, I think, like a combination of what Martin and what Daniel was saying. Maybe so we require to understand that we need to understand that there's different flavor to the mathematics that we need to understand, to implement causality. And for example, Julia Perl, both Julia Perl and Carl Friston talk about about the importance of manipulation and establishing necessary relations. So we have to say that we have to go beyond correlations, just what we call, I could also say it like, we could also call parallel relations, like parallel equivalent relations, or structural relations, which is what Michael was mentioning. If we need something else, if we need to understand, okay, this system has, for example, the causal power of this system is higher over this system B than vice versa, then you require, at least in the applications in your sciences or social sciences and so on, you need some kind of asymmetry, and not only in terms of time, but in terms of, as I say, this causal power. And causal power is a way more abstract thing than just, or at least complex thing that just input output in a function. You require this, for example, in, by the way, dynamical causal modeling, from Friston's perspective, uses basically a set of differential equations, linked to each other. And the idea is that, at least the very summarized idea, is that there's a way stronger influence from one node to the other than vice versa. This will mean that causality in this regard is more about how asymmetrical is the exchange of information. And then it's not necessarily that there's a different set of structural relations. We could say that maybe, for example, in a graph, the graph, the directed, so a graph defined as directed, non-directed, we can imagine like its topology, and then we imagine a directed graph, an equivalent. I mean, in some sense the topology is the same, but now you have asymmetrical flows of information. That's when you can begin to think about causality relations. Of course, there's many mathematical ways that you could implement this. It's not that this is beyond mathematics or whatever, but yeah, it's a bit more complex than just correlations. That will be the main comment to Michael's point. Michael, yeah, if you want.
Yeah. So information's a good thing to bring up here. And Martin Green is correct if like the universe does have a finite amount of information in it. But if the universe is truly analog in nature, you would definitely need an infinite amount of information to describe like the value of like space-time at like a single point. So, but thing is, it could still be analog, and that like our observations aren't necessarily like in contradiction to that like such an idea. And if it was analog and there like were no like branch cuts and it was well behaved, then the universe would essentially kind of be like super deterministic, and every point would have full information about every other point. So there isn't necessarily a flow of information when going from like point to point necessarily. I guess it's like kind of like a invertible transformation, you could think of it as. But it's all still there at each like point, maybe just arranged differently. Is causality even like well defined in something like superdeterminism?
If you have superdeterminism, that means that if you know what things are like at some time, if you've got a surface over which everything is known, then is known for all times. And so there's no change of information. And it's a very, very boring universe. The only reason we can actually have this conversation so on is that we're not constrained. This isn't a predetermined conversation. We gain new information from each other, from what's around us, and that new information is what enables us to be conscious and to live. So I want to come back to your notion, in terms of an analog universe. Again, I'll challenge this. I'm not saying the universe is analog or digital. What I'm saying is that it's limited in terms of its information content. So you can't resolve a point in space-time. There's no way that observationally you can resolve an arbitrarily small distance or an arbitrarily small time. And so these are mathematical conveniences, perhaps, for our calculations, but they can lead us into a bad place in terms of trying to understand what we're doing from a philosophy of science perspective, because we're talking about things that don't exist. And so think of all of the points of space-time as being fuzzy, and the fuzziness of the points of space-time may depend on what the density of local matter and local entropy is. If there's not much entropy out in the middle of nowhere, all you've got are CMB photons moving around, then the number of bits of information per cubic millimeter is about 1. On Earth or in stars and in dense matter, the number of bits of information per cubic millimeter maybe 10 to the 23rd or more, and so you've got information that's allows you to resolve fairly small distances, but the smallest distances we've been able to resolve so far are on the order of I think 10 to the minus 18 millimeters, and something like that. You can't go any smaller. That's with the LHC and CERN. So we slam particles together at an enormous energy, but we can only probe to a finite distance. We can't go to infinitely small distances.
Yeah, maybe. Oh, sorry. Just a side note, and maybe that's what I was thinking about. For example, quantum mechanics maybe is telling us that even if general relativity assumes a continuous space-time, we have to think that it is not, because maybe it's there's an actual minimum of resolution, basically, that makes sense, at least. Yeah. Michael, if you want to.
Yeah. So I take issue with the idea that if the universe was like predetermined, like GR might think it's like a block universe, that it would essentially just be like boring and like have trivial dynamics. I don't see why such a predetermined system would be able to have observers like us having a conversation such as this. And I do approach physics from a like relativist perspective. So I don't see any reason why we can't have like arbitrarily small like lengths and like times. Just because our like instruments aren't capable of like reliably observing such like scales does not mean that they fundamentally do not exist. I do not think that's a very good argument.
Yeah, if you allow me just briefly, my idea at least is that even if they in some sense exist, I do think that at the same time that not only us, but in general, any system has an intrinsic, some intrinsic limits in communicating with its environment. So maybe part of the imperfection of communication of information is intrinsic, and then that makes that effectively many systems are insensitive to many small or bigger or very big differences, and then practically, yeah, the resolution is not that high. That's my idea. And before Martin intervenes, if he wants, Daniel, I think you wanted to intervene a while ago.
I think I did, but now there's so many things have been said now that I'm just lost now.
Oh,
But it will come. It will come eventually, and yeah. So maybe you guys can keep on, and then I'll
Okay,
I'll come back to it.
in fact, do you have any
I was going to
intervention?
say the same thing you just said, because we had that conversation before.
Yeah, actually, yeah. We like Daniel, Fadi, and us, and I, us, had this and my collective system now have had this conversation about infinity in space and time, and several ways. And one of the things that was mentioned, maybe I don't remember who, but there was this slightly similar idea to some things that we mentioned. For example, the idea that maybe or maybe it was something that I was going to mention, comment on Michael's thought, that there's this possibility that if, and this has a very similar flavor to what Martin was saying before, there's this possibility that there's this at some point necessary convergence, maybe just because of the limitations of whatever, but yeah, of processing information or whatever. This convergence that even if that makes that even if there's not an intrinsic absolute determinism in terms of analytically continuable evolution of systems everywhere, even if we don't have that kind of absolute analytical continuability, um, the maybe a need for epistemological theoretical need for convergence, and not only epistemological. I also mean that maybe, as he was saying, if systems have also processing limitations for processing information, that may be literally the thing that is implemented everywhere. There's a need for convergence, and then even if sometimes there are weird things that could happen in the, at least in the possibility space, we see weird branches that could be possible. Those are not going to be chosen because of this need for convergence and continuation. That's one idea that may link what Martin was saying before
Yeah.
with
And
Michael's.
I was going to comment on that. Even though that's the case, you might still have some runaway branch, which for some reason just runs away with the possibility space, because it's just an explosion of usefulness there in some sense. Um, so that would be the one that persists. So even though you have like a sense of convergence, you might still have the sudden unexpected thing that happens, that convergence is not there, but it is somewhere else to some other point.
One idea there could be, and then I leave the floor to anyone else. Maybe that's somewhat within some constraints, constantly happening, and that's why, yes, in absolute terms or universal terms, entropy increases, but there can be fluctuations of it. And of course, let's also remember that, and this comes from 19th century debates, and that like, and the idea of the what we call entropy nowadays, and the second law, and they talk about probabilities. They never say that something is intrinsically impossible. So yes, constantly something happens because it's the most probable thing to happen, but there's, at least so far, there's nothing prohibiting that in 1,000 trillion years there's this spontaneous opening of possibilities, amazing explosive amazing explosion of branches towards more possibilities. So yeah, what you say is, I will say, is quite compatible with thermodynamics,
Yes.
at least today. Yeah.
It's always possible that glass I dropped on the floor will pop itself back up and put itself back together. It's thermodynamically unlikely.
Exactly.
Yeah,
And
that,
you know,
oh, sorry.
the,
Oh,
the,
no. It's just that like part of this conversation feels very like it seems to be more about the philosophy of what theories we want to like entertain or not, in the sense of because even if there's entropy, entropy is just some statistical artifact or whatever, and there's the possibility that a glass could reorganize itself after I break it or whatever. From the practical and ecological, human being reality, it's not really that useful. So do we entertain the idea that that's a possibility, or do we just reject it because it's inconsistent with our observations? Like, and it's just more like a theoretical kind of toy thing that we can, I mean, until we get, I guess, some sort of way to replicate that, right? Way to create that scenario where entropy is undone. It's ecologically not useful for us from the point of view of creating reliable theories and that create these deductive connections with empirical data and all this. I don't know if I'm explaining myself very, very well, but yeah.
Yeah.
I think you have. You asked me, what kind of theories do we want, or what's useful as a theory, and I think the answer is that a theory is useful if it can be tested empirically. So if you've got a theory and predictions of a theory that have no empirical tests, then this is just something. It's a theory. It's a model you've got in your mind, but you have no way of determining whether it's correct or sensible, because the consequences of that theory are beyond any possibility of testing. So it's just an idea. It's not a scientific theory. A scientific theory, to be considered useful, needs to be testable.
Wait, I'm ticking.
Sorry?
I'm ticking down the time.
Oh, wow.
Sorry.
His clock is on.
Oh, I'm sorry. I confused Martin with Michael. I'm sorry. Yeah. I'll take that into account in any case. Yeah, I'm sorry.
Yeah. So I mean, that's all I'm saying when I talk about not being able to resolve arbitrarily small distances, so on, that we have no possibility of testing the such consequences of things that would happen at tiny distances, or infinite derivatives and so on, and therefore from a theory perspective, it's not useful.
Yeah.
That's what I would usually think is it's more like a theory it has to be ecologically useful. So me as an animal, it has to give me something, not merely just explain things away and give me some satisfaction, but just like doing something more than that.
Yeah, that's why the connection that I always try to make, even if I'm discussing very abstract, like very in a very abstract way, information theory or thermodynamics, and is trying to say, okay, if the universe is like a brain as like a cognitive agent, I have to relate this kind of assumed constraints with intuitive constraints of that humans have. That's why I've tried to make all these parallelisms. So yeah, but yeah, I think we all agree in that in that spirit. Michael, if you want to take your time now, literally, if you want to intervene.
Okay. I would like to say that I don't really think space-time is necessarily well defined at okay. So I think a realistic space-time it is probably best thought of in a coarse-grained manner, because if you start thinking about it in with all the detail, then I think that for a realistic space-time, which is probably quite noisy on lower levels, it would probably the Levi-Civita connection would probably not even be well defined at a single point. If you look at the background behind me, that is essentially the Levi-Civita connection of a one-dimensional fractal space-time essentially. And if you just like this is like the scale the like dependent connection. If you were to just like zoom in, you like it would just get like more and more detailed. And if you looked at the one that was defined point-wise, it's just like pure like random noise. Like so I think it's a good thing to like bring up. Also regarding entropy and like the second law, um it might not really be like if you were to have a like space time with like a bunch of like closed time like curves in it, the notion of like what direction is like necessarily like counts as forward in time might become like ill-defined, and it's possible that like the second law might kind of like break down in such a hostile environment because general relativity tends to be like hostile for like various different things like conservation laws. So I could see something like that occurring. Just figured I'd bring that up.
I will. That's also why I'm quite concerned with. So, but saying otherwise, that's why I'm quite motivated about the idea of something about entropy and information theory to be quite somewhat tautological in the epistemological sense, that maybe we are just defining. Okay, if for example, an example from that I of thought that I had several years ago, it's that we tend to say, yeah, systems tend to be stable, or systems tend to want to be in stable states. At least in when spreading science, these kind of things are said. Maybe that's just a very self-convincing way to describe things. Maybe when they become, for example, when they become more predictable, um, we say, okay, that's what they want to be, what they want to do. But it's just that we or any other system, maybe that, and that's the funny thing, wants to become more predictable, and that's why we say it wants to be stable. So maybe that's the kind of thing that helps uh, reality not to break apart. Not that this actually is makes takes an effort. It's just a way to say that maybe that's why many weird things that could happen in some abstract space don't actually happen. Fadi, if you have any, we'll finish after your last you will intervene if you want. So just asking you.
No. I think the things we said in the conversation, like last time, are the things that we've already mentioned. So I'm happy with.
Yeah. Well, if you want to mention for other people at least one of the things,
I mean, at least on the this is not really about the asymmetrical information flow, I guess. But one of the things we also mentioned was um, on uh, on going into finer and finer details. Like one of the ideas I had was something like you might be able to, as long as you're able to gather the energy to go into smaller and smaller details, but in some sense you're creating the details while you're going there as well. They might not necessarily be there before you go there. The moment you start interacting with it, that's the moment these details start appearing there. So they don't actually have to be in some infinite precision there, but the moment you start exploring there, that's the moment you see the
like
see.
fractal quantum mechanics.
Exactly.
Maybe.
Um,
Kill
so
Martin, yeah.
yeah, no, but I think that's the main thing. Some
So just,
other,
yeah, sorry.
yeah. No,
Just
no, go ahead,
to
go ahead.
pick up on that one thought, this is what we do with our particle accelerators. We collide tiny particles together at ever greater energies, and because we're putting so much energy to get into these tiny distances, we create all kinds of new particles, and it becomes more complex.
Yes.
That's a good point. That's a very good point. We more or less we exaggerate things to be able to study them, but it's like trying to study an insect by making it huge, basically. Very, very coarse analogy, but so yeah. And Danny, if you want to make one last intervention, if you have anything to say.
Nothing particular. Just the last thing you said. I think that's true of all science in general. Like you gather a lot of data, and to get insightful knowledge, what you do is simplify or like the information to some extent. You do like some regression, linear regression. What you do over a cloud of points, you do a line, and that line represents a better understanding, more actionable understanding for you. And I guess yeah, that's the only thing I would say. That's just human thought happening.
Yeah, literally like an exchange, a trade-off of an informational trade-off, basically. So Martin, if you want to make one last intervention.
No, I think I've said enough. Thank you.
Oh,
Great.
yeah,
And
think about
Michael?
your comment about like quantum fractal stuff reminded me of an article I saw in like Quantum Magazine, titled where some sea string she sees a space-time made of fractals. And essentially it's this idea that like particle physics might, I think if I remember correctly, particle physics might become kind of self-similar when going onto smaller and smaller scales. And that could result in some fractal dynamics popping up. So just, I put the link in chat, by the way.
That's a very interesting thing. So for the rest, I was trying to write the link in the YouTube chat, but it won't allow me, like my mobile phone. But it's basically an article from Quantum Magazine called "Where Some Strings." Well, I don't know the name.
Where
Let
some
me-
C
yeah,
string, where some C string, she sees a space-time made of
space-time made of
fractals.
fractal. Thank you so much. So yeah, that's our last thing. Thank you so much for this very, very delightful discussion. It was it was less crowded than I wanted, because I always want more people, and I insist all the audience, both now in time, or if you see the streaming in the future, you can join it. It's a friendly space. We're not going to make fun of you. Well, I always do the opposite of it. Sometimes people say, "Oh, I'm thinking what I'm saying is bullshit." No. There's always a valuable insight to be said. Thank you so much, Martin. Yes, you want to say?
No, I thank you. I think it was, I got your reminder this morning, and that was good.
Thank you so much for coming. Yeah. And now, when you in your first intervention, when you were mentioning these ideas, then I recalled. Yes, I've seen videos of you like from earlier videos
Yes.
in SEMF. I love them. Thank you so much for
Yeah.
your previous contributions too. This community is already has a long history. Despite the YouTube channel was hacked, that's why the videos are no longer there. We are trying to recover everything, talking with Google, and we saved some things. We are going to progressively upload the things that we have again, of course, because I hope that your videos are preserved too. And in any case, we are going to generate more, of course. We're going to have next Concept Colliders in, I think, 2 weeks. But in general, the idea is to have one of these every 3 weeks, and alternate rigor, causality, and cognition. And of course, please consider joining the Discord, because there's this very long list of channels to discuss everything, literally everything, even job applications in science. I sent one the other day about one in Madrid. And join the summer school, because it's going to be great. We have again great speakers. Not all of them are confirmed yet, but the ones in the website are confirmed yet already. And we have and again a very international set of speakers. So thank you all the people in the call. Thank you so much for coming. Later or sooner, Michael, thank you so much for coming. And yeah, see you next time.
Sorry, I showed up late.
I know.
See you. Bye.
Bye-bye.
Bye.